Welcome to chemistry classes. In this video we are going to discuss about D and F block elements. In this video we are going to discuss about grade 12 chapter 8 D and F block elements. Okay, so here we have to understand first position of D and F block elements in periodic table. Position of D block elements and F block elements in periodic table. You can see here this is the structure of periodic table and you can see the position of D block elements. Here D block elements are between S block and P block. Actually the position of D block in the middle of S block and P block. Okay, P block elements D block elements also called transition elements. D block elements also called transition elements. Okay, in D block elements after lanthanum. Okay, elements coming after lanthanum. You can see in periodic table in bottom part there are two period. Here first one lanthanide and second one actinide. Lanthanide and actinide together it is called F block elements. Okay, elements which coming after lanthanum it is lanthanide. Okay, elements which coming after actinide it is actinides. Okay, so this lanthanides and actinides together we will call F block elements. F block elements. Okay, here in D block elements you can see in periodic table group 3 to group 12. The elements which coming between group 3 to group 12. These are D block elements. Okay, these are D block elements. D block elements are between group 3 to group 12. Also the important metals such as silver, gold, platinum, copper, iron, this type of elements are coming in D block elements. Most of the most important metals such as silver, gold, platinum, copper, iron, this type of metals are coming in D block elements. D block elements are called transition elements. D block elements are called transition elements. Okay, also F block elements are called inner transition elements. I told you D block elements are called transition elements. Similarly, F block elements are called inner transition elements. Clear? Look here, in D block elements you can see in D block elements there are three period. First period elements are called 3D series. 3D series, 4D series, 5D series, because their general electronic configuration coming 3D forest. Okay, the outer shell electronic configuration of first series of D block elements and 3D forest. Similarly here 4D 5s, here 6D, here 5D 6s. These are the electronic configuration. These are the outer shell electronic configuration of these elements. Okay, so first period and 3D 4s, here 4D 5s, here 5D 6s. That's why the first period of D block elements are called 3D series, here 4D series, here 5D series. Okay, so here in F block elements you can see two period. Okay, so these are called 4F series and 5F series. 4F and 5F series. Okay, and here 3D series elements are starting from scandium to zinc. In D block elements first period mean 3D. 3D series are starting scandium to zinc, and here 4D series ytterbium to cadmium, and 5D series lanthanum to mercury. Okay, these are the general introduction about D and F block elements. Okay, next one we have to learn here D block elements. We have to study here D block elements or transition elements. Okay, so here general electronic configuration of transition elements n minus 1 D 1 to 10 electron, n is 1 to 2 electron. Here general electronic configuration, this one example for electronic configuration I told you before, 3D 4s, 3D 1 to 10, 4s 1 to 2. Okay, this is the general electronic configuration for this is the first period. For example, 3D series, this is the electronic configuration, 3D 4s, 3D 1 to 10, 4s 1 to 2. Similarly 4D series, 4D 5s, okay, 4D 1 to 10, 5s 1 to 2. Similarly here 5D series, their general electronic configuration, 5D 6s, 5D 1 to 10, 6s 1 to 2. Clear? So this is general electronic configuration. See here this metal, zinc, cadmium, mercury. Zinc, cadmium, mercury, we know these elements are in D block elements, but they are not considered D block elements. Zinc, cadmium, mercury, these elements not considered as D block elements because they have complete D electrons. We know D subshell. Look here, 1, 2, 3, 4, 5. Okay, so they have complete D electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They have completely filled D electron. Which elements? Zinc, cadmium, mercury. That's why these elements do not show any properties of D block elements. See here, D block elements with partially filled D orbitals. Partially filled D orbitals mean D block elements with incomplete D electron. For example, incomplete D electrons mean, look here, this is one example for incomplete D electron. Incomplete D electron. Okay, so here it is completely filled. Here these are vacant. There is unpaired electron. Here no unpaired electron. So this type of D block elements, they shows different properties such as they have variable oxidation state, they act as catalysts, they make colored complex, okay, and they have paramagnetic properties. This type of properties showing D block elements with unpaired electron. Okay, but here zinc, cadmium, mercury, they have completely filled D electrons and they do not show this type of properties and they are not considered as D block elements. So which elements not considered as D block elements? Zinc, cadmium and mercury. Okay, and which type of elements showing this type of properties? D block elements with unpaired electrons. Okay, incomplete D electrons, D block elements with incomplete D electrons, they showing this type of properties, variable oxidation state. These D block elements act as catalysts, okay, and they make colored complex, okay, this type of properties. And here zinc, cadmium, mercury not showing this type of properties. And here general electronic configuration of D block elements, n minus 1 D 1 to 10 electron, ns 1 to 2 electron. Clear? Okay, next one we have to discuss here general properties of D block elements. General properties. In general properties, first one we have to discuss here physical properties. Physical properties of D block elements or transition elements. Here D block elements, they make colored compounds. D block elements, they make colored compounds. D block elements, generally D block elements have very high melting and boiling point. D block elements, they have very high melting and boiling point. Okay, most of these elements are metals with a high melting and boiling point. There is one exception case, mercury. Okay, mercury, it is liquid state at room temperature, but rest of them very strong metal, very hard metal, they are solid state at room temperature. Okay, and another one here, D block elements, they are malleable and ductile. We discussed here they are metals and they are malleable and ductile. Okay, they are malleable. Malleable mean we can change these elements, we can change this metal to thin metal sheet. Okay, so they are malleable, also they are ductile. They are ductile mean we can convert this metal to thin wire, metal wire. So here D block elements, they are malleable and ductile. Okay, and here they are good conductor of electricity and heat. They are metal and they consist of free moving electrons. That's why these D block elements, they are good conductor of electricity and heat. Okay, so here we discussed here general properties of D block elements. Here they have high melting and boiling point. They are malleable and ductile. Okay, and here D block elements, most of them are metals and they are good conductor of electricity and heat. Okay, and here they have high tensile strength. They are hard and they have high tensile strength. Okay, and they produce sound. They are metals. Okay, when you put this metal down or you beat two metals together, they produce sound. It's mean they are sonorous. They are sonorous and they have metallic luster. This metal, they are shiny. They have shiny. That's mean they have metallic luster. Okay, and here we have to understand another point. The melting and boiling point of 3D, 4D, 5D series increases with the increasing number of unpaired electron. Okay, here melting and boiling point of 3D, 4D, 5D series of D block elements increases with the increasing number of electrons. Okay, increasing with number of unpaired electron till D5. Okay, so here melting point and boiling point of 3D, 4D, 5D series increasing with D1. Imagine you have D1, D2, D3, D4, D5. Okay, so here after D5, imagine one D orbital which contains 6 electron, then it will be 1, 2, 3, 4, 5, 6. Now unpaired electron decreased. In D orbital, if there is 6 electron, so the configuration coming like this. So how many unpaired electron here? Here number of unpaired electron 4. Okay, so here number of unpaired electron in D orbital D1, D2, D3, D4, D5. After D5 again it will change D4, D3, D2, D1 like that. Because after D5 pairing occurs and number of unpaired electron decreases. So here we have to understand here melting and boiling point of D block elements increases with increasing number of unpaired electron, accordingly D1, D2, D3, D4, D5. So which element showing high melting and boiling point? Here high melting and boiling point, the metal or element with the D5 configuration shows high melting and boiling point, then D4, then D3, then D2. Okay, so after D5 melting and boiling point of d block elements decreases gradually because number of unpaired electron decreasing. Clear? Here there is one exception case, manganese and technetium. Manganese and technetium, they showing exception case, rest of the elements showing this trend. Okay. Also we have to understand here bond strength. Bond strength of d block elements also increasing with the number of unpaired electron. Elements with more number of unpaired electrons showing more bond strength. Okay, because there is more unpaired electrons to involve chemical bonding and showing more bond strength. So these are the general properties we have to understand here. Here we discuss here d block elements. They have high melting and boiling point. They are malleable and ductile. They are good conductor of heat and electricity. They have high tensile strength. And this d block elements, they sonorous and metallic luster, and melting and boiling point of 3d, 4d, 5d series of d block elements increases with increasing number of unpaired electron. Okay, so here d1 to d5 it will increase. After d5 melting and boiling point gradually decreasing. Here except manganese and technetium, all other elements showing this trend. Okay, also bond strength increases with the increasing number of unpaired electrons. Clear? Okay, next one we have to understand here atomic and ionic radius of d block elements. Atomic and ionic radius of d block elements. See here we have to understand generally ions with the same positive charge. Ions with the same charge in a period, okay, they shows progressive decrease in ionic and atomic radius. Ions with the same charge in a period, they shows progressive decrease in their atomic and ionic radius. General case, we are talking general case, not in d block. Generally ions with the same charge in a period, their atomic and ionic radius decreases progressively or decreases gradually in same way. But in d block elements, their atomic and ionic radius are very close, or their decrease very less extent. Also, when you see this diagram, atomic and ionic radius of 4d and 5d series are very close each other. We know in d block elements there are 3d, 4d, 5d. So atomic and ionic radius of 4d and 5d series are very close each other. Also in 3d their ionic radius difference is very less. Okay, very less difference. So why it is happened? This is because of lanthanide contraction. Lanthanide contraction mean we know the actual electronic configuration, general electronic configuration of d block elements n-1 d 1 to 10 ns 1 to 2. Okay, but in 4d series and 5d series there will be f block. Okay, n-2f. So before filling this d orbital, f orbitals are filling. Okay, before filling d orbital, f orbitals are filled by electrons. Okay, that's why this process happening. Clear? So here the variation of ionic radius quite small. Also here you can see 3d and 4d series, you can see their decreasing atomic and ionic radius. There will be a curve will be observed. A curve you can see in the graph. So this is because of the lanthanide contraction. Lanthanide contraction means 4 of orbitals are filled. 4 of electrons are filled before filling 5d. Before filling 5d orbitals, 4 of electrons are filling. That's why here atomic and ionic radius of 4d and 5d series are very close each other, and there is one curve is observed. Okay, and this process is called lanthanide contraction. Also, we will study more details about lanthanide contraction. We have to study F block elements, and we will study more details about lanthanide contraction. Here you just understand here, before filling d orbitals, F electrons are filling. That's why here this F orbitals shows less shielding. F orbitals are showing less shielding. Okay, so nuclear charge, effective nuclear charge can affect outer shell electron more effectively. That's why this process happening. Clear? So here next one we have to discuss here ionization enthalpy. Generally we know from left to right in period, atomic number increases, number of protons increases. So effective nuclear charge increases. Therefore, ionization enthalpy increases from left to right in 3D series. In d block elements, ionization enthalpy increases from left to right because effective nuclear charge increases. Okay, but here first ionization enthalpy of d block elements do not increase steeply such like main group elements. We know in main group elements or p block elements, first ionization enthalpy increases steeply, but in case of d block elements, first ionization enthalpy do not increase steeply like in main group elements. In main group elements mean p block elements, it will increase steeply, but d block elements not. Okay, so these are the things we have to understand about ionization enthalpy. Next one we have to understand here oxidation state. Next point we have to understand here oxidation state. D block elements shows various oxidation state. D block elements shows various oxidation state. Okay, so here various oxidation state mean one element shows many oxidation state in D block elements. So here elements in the middle of D block elements, in the elements which coming in the middle of D series, they shows maximum number of oxidation state. For example, you know, in 3D series, you know, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So here manganese coming almost in the middle of this series. Okay, so in 3D series, manganese coming in the middle of D block or in the middle of series manganese, and this manganese shows maximum oxidation state. In 3D series, manganese shows maximum oxidation state. Maximum oxidation state mean from +2 to +7, +2, +3, +4, +5, +6, +7, like this maximum oxidation state by manganese. So here generally you understand the elements which coming in the middle of D series, they shows maximum number of oxidation state here manganese. Clear? Okay, so here we discuss elements which coming in middle of D series, they shows maximum number of oxidation state. Now we have to discuss here elements which coming each end of the D series, they shows very few number of oxidation state. Elements which coming in the middle, they shows maximum number of oxidation state. Also the elements which coming in each end of D series, they shows less number of oxidation state. Okay, see here example, here scandium and titanium. Scandium and titanium, these are coming in the beginning, okay, and they have few oxidation state. Why these elements have few oxidation state? Elements, these elements are in the beginning. Scandium, titanium, they are starting a 3D series, in the beginning of 3D series. Okay, you know 3D series starting like this. Here scandium, titanium, vanadium, chromium, manganese, iron, copper, nickel. Here cobalt, nickel, copper, zinc. So here scandium and titanium are in the beginning, okay, and they have few number of electrons. They have few number of electrons in their outer shell. So they have few number of electrons to lose. That's why this element shows a very less number of oxidation state. Now we are talking here elements which coming each end mean here and here, okay. So these elements here, copper, after copper, zinc, okay. So the elements which coming each end, they showing few oxidation state. Here one example, scandium and titanium, they have few number of oxidation state because they have less number of electrons in their outer shell. So less number of electrons to lose. That's why this element shows less number of oxidation state. Similarly here, next point we have to discuss here, copper and zinc. The elements which coming end of this series, copper and zinc, they shows very less number of oxidation state. Why this element shows very less number of oxidation state? Because here these elements, their outer shell, they have so many electrons in their outer shell, and there is no vacant orbit. There is no vacant orbit for electron sharing. To make new bond, there is no vacant orbit or very less number of vacant orbit. That's why this elements also shows very less number of oxidation state. So generally we will say here the elements which coming each end of D series, they showing less number of oxidation state. In the beginning they have less number of outer shell electron to lose, okay. At the end they have maximum, they have so many number of electrons in their outer shell, so there is no vacant orbit to make overlapping or to make electron sharing, okay. So this is about number of oxidation state. Look here, next one we have to discuss here in p block elements. In p block elements, heavier elements shows lower oxidation state. In p block elements, heavier elements favored lower oxidation state. P block elements, example here, carbon, silicon, germanium, tin, lead. This element shows +4 and +2 oxidation state. But heavier elements like lead, we know lead, the most stable oxidation state of lead is +2 oxidation state, not +4. But we know carbon, silicon, germanium, they showing +4 oxidation state. So here in p block elements, heavier elements favored lower oxidation state, lower oxidation, +2 and +4. So +2 is lower oxidation state, heavier elements favored +2 oxidation state. But this statement is exactly opposite in D block elements. In D block elements, this statement is not true, okay. For example, see here in group 6, molybdenum, tungsten, molybdenum +4 oxidation state of molybdenum and tungsten is less stable, okay. Here in group 6, molybdenum and tungsten found to be less stable, +4 oxidation state of molybdenum and tungsten found to be less stable than chromium +4. Okay. Okay, see here, these are metal carbonyl. Here, nickel tetracarbonyl, iron pentacarbonyl, these are metal carbonyl. Okay, we learned metal carbonyl in grade 11. So in this type of compound, here oxidation state of nickel and iron, oxidation state of nickel and iron is 0. Oxidation state is 0. So these are the things we have to discuss in this video. So here we learned some introduction about D block and F block elements, D and F block elements introduction, and we learned some properties of D block elements, their physical properties, oxidation state, ionization enthalpy, okay, atomic and ionic radius. These things we discussed in this video. So you can review this video once again. Okay, rest of the things we will discuss next class. Okay, next video we will discuss rest of the things. So thank you for watching this channel.